Hi, good morning. My name is Dr. Terence Leung. I'm an associate professor in biomedical engineering at UCL. So today I'm going to say a little bit about our course and also a particular medical technology. So we want to find out how do we use Fitbits, Apple Watches, and mobile apps to measure your heart rate. So now, before we begin, maybe let's have a look at whether everybody is here already. Okay. Right, so we have 15 people so far. Okay. Okay, so we have quite a lot to go through today. So perhaps I can start the talk. Okay, so now, first of all, I would like to introduce some helpers. First of all, we have Miranda. Miranda, would you like to switch on your camera? Yes, hi, Miranda. So Miranda is going to help me to do an online demonstration. You'll find out what exactly we're going to demonstrate later on. And next we have Yifan. Hi, Yifan. Hi. So Yifan is also going to help us to do this demonstration. And thank you, Yifan. So both Miranda and Yifan are doing their PhDs with me. And we are very happy for them to be able to help us today. Okay, so now let me start the talk by sharing my screen. Okay, now I don't know how many of you have Fitbits or an Apple Watch, or perhaps a mobile app that allows you to measure your heart rate. So we're going to find out exactly how this technology can measure your heart rate. Okay, so now, first of all, why is heart rate important? Why do we want to measure it in the first place? Now, it turns out that heart rate is an indication of your health. So for people who are healthy, the heart rate is between 60 to 100 beats per minute. Sometimes if we are a little bit stressed, the heart rate may be a little bit higher. And but then if you are resting and you are not very anxious, and yet you still have a very high heart rate, then perhaps is an indication of infection or anemia or other problems. Now, not necessarily related to your hearts, okay? If your heart rate is low, and very often it means that you are very healthy. So a lot of athletes, people who exercise every day, they have very low heart rate, something like 50 something heart rate, 50 something beats per minute. And so sometimes low heart rates can mean a good health. But of course, some people with heart problems, they also have very low heart rate. Now, why people want to use Fitbit? They want to measure their heart rates during exercise, right? So this is another way to measure your fitness level. People want to know that when they exercise, surely their pulse rate will go up. But is it like really high, like 160, 170 beats per minute? If that's the case, that's a little bit too high. So people want to track their pulse rates during exercise. Okay, now, so how do we measure heart rate? Very simple. We know that you can feel your own pulse on your wrist, somewhere here. Now, this is basically the radial artery. So if you just feel your radial artery, and then you count how many pulsations there is during 1 minute, then you know your heart rate. So that's beats per minute. Okay, so that's the simplest way to measure your heart rate. What about measuring heart rates with lights? That's slightly difficult to understand, right? Because surely lights is blocked by tissue, right? How are we going to actually use lights to measure pulse rate? Can light even pass through human tissue, right? Now, in fact, to answer this, maybe you can do an experiment. If you have a smartphone, maybe you can try to switch on the LED, okay, like the one that I have here. And if you put your finger over it, okay, so what it is actually you try to block the LED light with your finger, but in fact, some lights can still pass through your finger, right? As you can see, even if I block the LED lights, my whole finger actually glows. It's actually possible for lights to penetrate through human tissue and then reach the other end of my finger. Okay, so you can see that in fact, human tissue is not as opaque as you may think. They are actually quite transparent. Okay, so let me just switch off my LED. Okay, so how are we going to use lights to measure heart rate? Okay, now, so a little bit of theory now. So what we see here is human tissue, okay? So we have a light source here. That's our LED light source I just demonstrated. And then if let's say we detect the lights at a certain distance away, then what happened is we are going to detect the lights that has passed through the human tissue, okay? So it turns out that the lights that is detected by a detector over here from a light source here, the light propagation has like a banana shaped kind of pattern here. So if we happen to have a blood vessel in this field of view, then we are going to pick up what happens to the change in blood volume in here. Okay, so just imagine that if the blood vessel is pulsating because of the arterial pulsation, so the light is going to be able to pick up the the blood pulsation. Okay, now by the way, this is what we call reflection mode. It means that the light source and the light detector, they are both on the same plane. Okay, now one thing we want to know is what kind of light is suitable for measuring pulse rates in the tissue. Okay, so in order to answer that, we need to have a look at the absorption spectrum of oxy and deoxyhemoglobin. So we know that in tissue, the main absorber is optical absorber is actually blood. And then inside blood, we have hemoglobin, and hemoglobin absorb a lot of light, okay? And in fact, the hemoglobin absorb light differently if they are oxygenated, okay? So we see that both oxygenated hemoglobin and the oxygenated hemoglobin, they absorb light differently over the wavelengths from 300 to 1000 nanometer here that we are looking at. And then in fact, from 400 to 700 nanometers, this is the visible light range. So this is the light that we can see with our naked eyes. Now, beyond that 700 nanometer, we can't see those lights with our eyes. Those are the near-infrared light. Okay, so the first questions that we are wondering is what kind of wavelengths should we use as the light source, right? Okay, so quite high absorption here at the violet lights range, and then the absorption is less in the red light range and also the infrared light range. Yeah. So what kind of light should we use? Should we use violet light, blue light, or green light, or orange, yellow, or red? Okay. Now, so it turns out that we can't really use violet light because what happens is the absorption is very high. For violet light, what it means is if we use violet light, the hemoglobin will absorb all the violet light, and the violet light cannot actually penetrate too deep into the tissue, never mind being detected at a certain distance away. Okay, so violet light is not a good idea. So what about green light? Now, green light is actually, it has certain absorption, but it's actually lower than violet light. So green light is actually not a bad idea because it is, so hemoglobin is very sensitive to green light. So we can actually use green light. And although a certain green light may be absorbed, but the absorption is still low enough for the detector to detect this green light at a distance away. Okay. Now, what about red light and near-infrared lights then? They are actually even better because they have lower optical absorption. It means that these red light or near-infrared lights, they can actually go deeper without being totally absorbed by the hemoglobin. So if we use red light and the infrared light, we can probe even deeper into the tissue. Okay. Okay, so is that all? There's one more criterion we're going to look at later on. Now, so in terms of where you put the light source and detector, apart from putting both on the same plane, in fact, you can put them, if the geometry allows, you can actually put the detector on the other side of the tissue. All right. So we have this kind of geometry in a finger. So this could be one side of the finger. This could be the other side of the finger. So in that case, we have this transmission mode here. All right. Okay. So now, what do we mean by light source? Light source could be a LED. Okay. So this is the kind of LED. The LED that you use in your smartphone is actually smaller than this, but you can use LED as the light source. And then for the light detector, we use electronic component called photodiode. All right. Okay. Now, so we have to be careful with our light detector. So we want the light detector to only receive light from our light source. Okay. Now, what do I mean by that is if I have a photo diode as our light detector, we want the photodiode to measure the light coming from the skin alone. Okay. And so if we kind of put the photodiode kind of up in the air, then the photodiode may actually detect light from the room lighting, from the surrounding, and the whole technique wouldn't work. Okay, so we want to make sure that our light detector only receive light from our light source. Okay. Right, now let's have a look at an example. Okay, this is a pulse oximeter. So I have one here with me. So this is a portable one that I have. And what happens is you put your finger inside the pulse oximeter, right? And so over one side of the pulse oximeter, we have a LED light source. And on the other side, we have a light detector. And that's normally a photodiode. Okay. And so remember that we want to make sure that the light detector only receives light from the tissue, right? So how do we do that? So this is a schematic of the pulse oximeter. So once again, this is the pulse oximeter. This is the LED light source. This is the photo dart sensor. This is your finger. Over here, we only focus on one particular artery. And you can see that during systole, when the heart contracts, there's more blood in the artery. So that's why the artery is thicker. And because there's more blood in the artery, less lights comes out from the other side, yeah, because more light has been absorbed by the hemoglobin inside the artery. Okay, so this is what happened during diastole, when the heart relaxes and there's less blood in the artery, and there's more light being able to transmit it through the artery. Okay, now, so coming back to the question of how do we make sure light detector only receive lights from the tissue? And you can see that the design of the pulse oximeter is such that you put your finger over the photo dart sensor. Okay, so that's why the photo dart sensor cannot detect light from the room or from other surrounding lighting. Okay, so that's how we make sure the light detector only receive light from the tissue. Now, next question is what kind of light should we use? So once again, we're not going to use violet light because we're not going to get a lot of light transmission if we use violet light. So in this case, we normally use red light and infrared light. Okay, so because in this case, we make sure that we have enough red and infrared lights that can pass through the finger without being totally absorbed. Okay, so this is how pulse oximeter measure pulse rate. Now, what about an Apple Watch, right? So if you have an Apple Watch, look at the other side of the Apple Watch, you will see that there are some LEDs here. Now, although you are seeing the LED in red, but in fact, the LED can also be switched on as green and also infrared, okay? So red, green, and infrared. So we understand why, right? Because we can have green, we have a strong, hemoglobin has strong absorption of green light, so that make the light sensitive to the change in the concentration of hemoglobin. And also we can use red and infrared light, right? And next to the LED, you see that there are some detectors. So there are some photo diodes here, okay? Now, one difference between this setup and the pulse oximeter setup is, of course, is about the mode of detection. So this is actually a reflection mode, okay? Now, because this is a reflection mode, we want to make sure that the light source and detectors, they are closer together in order for the lights to be absorbed, to be able to transmit it without being totally absorbed. Okay, so this is the setup for Apple Watch. Now, next, we're going to have a look at FitBit. So once again, we're interested in the other side of FitBit, okay? We are interested in the sensor. So once again, we see that we have two LEDs here. This time, the LEDs are using the green light, and then the detector is in the middle, okay? So once again, this setup allows the change in blood volume in the artery being detected by light. Okay, so now a question for you. So far we have been saying that we use the photo dart as the light detector. But can you think of any other light detector that we can use, something that you know quite well? And we have to make sure that the light detector only receives light from the tissue, okay? Can we use perhaps a camera? Yeah, camera, detect lights. So should we use a digital camera? Well, if we use a digital camera, we take a photo of let's say the skin. That's fine, but then we cannot make sure that we only detect light from a particular spot in skin, which accounts for the light that comes from a particular light source, right? Okay, so this is probably not a good idea. What about the camera on your smartphone then? Can we use the digital camera on your smartphone? Yes, in fact, you can, because once again, you can just cover the camera with your finger, right? In that case, you make sure that all the lights that is detected by the camera, they have paths through your finger, right? Not from some other light sources. So all the light that you detect has propagated through your finger, and that's exactly what we want to measure. All right, so we can do that now. So this is why you can use a smartphone app to measure your pulse rates. And this is a very popular app, and you may have this app on your smartphone too. This is called Instant Heart Rate app. So question for you. What is the light source we are using? Okay, so previously we know that for a pulse oximeter, we're using the red light and infrared light. And then Apple Watch and FitBit, they use green lights and red light and infrared light. What about this? Okay, so what happened is normally this kind of app, they switch on the LED light, which is just white. Okay, so exactly what kind of light source we're using then? The answer is actually, because it's white light, we have all colors of light. Yeah. So in fact, it's all the light here. So in that case, how are we going to extract maybe the green lights or the red lights then? Okay. We'll come to that a bit later. Another question for you. In this case, are we talking about a reflection mode, whereby the light source and the detectors are on the same plane? Or are we talking about transmission mode, when the light source and the detectors are on the opposite plane of the object? Okay, surely it's transmission mode, right? So what we're talking about is you cover the camera with your finger. Okay, so the detector is here, that's your camera. And then light source just comes from your room lighting, or maybe LED. But anyway, so the mode of propagation is still transmission mode. Okay. Now, so if we use the camera to be the detector, what is the camera actually measuring? What is it actually getting then? Right? Okay, so this is a photo of a baby. This is for different research. So basically, let's say if we use webcam to take a picture of a person, and then if we really zoom in, look very closely to the pixels, yeah? So what we find that, in fact, each pixel is captured by actually four different color sensors. Two of them are green sensor, and then one is red and one is blue. Okay, so what happens is, in fact, we cannot detect all the lights in the photograph. We only capture three types of light. So in fact, a color picture consists of three combined together. a red picture, a green picture, and a blue picture. Okay, so if we only analyze the red picture and also the green picture, then we can get our optical measurement, right? So just like before, although before we actually use red light and green light, but now we basically use white light, but we only detect the red part of the light and the green part of the light. Okay, so we then go on to write a computer program, and we can then build this program that can measure heart rates using a webcam. All right, so this is our program. So what happened is we can then put our finger over the webcam, and then the webcam will only see red. Now, why is it red? Because of course, once again, hemoglobin absorbed all the light except red, right? Because hemoglobin absorb very little red light, so that's why blood looks red. And we have a picture like this. Okay, so if we kind of add up all the pixel values, and we are going to get this pulsation waveform, right? And at this point, we carry out a processing technique called Fourier Transform. So if we carry out Fourier Transform, we can turn this time domain signal into a frequency domain spectrum. And then we see a very clear peak here. So this peak happens at 1.5 hertz, which is the frequency of this periodic signal here. Okay, so by using Fourier Transform, we can get your pulse rates, and then if we times 60, we get the pulse rate at beats per minute. So that's 90 beats per minute. Okay. Now you may notice that there's like a baseline variation here. That's something related to your breathing, and also a 10-second cycle, which is related to your nervous system, central nervous system. But that's another topic. So this kind of signal that we measure using lights is called photoplethysmography signal, or PPG. Okay, so this is why we can actually use a webcam to measure your pulse rates. Actually, what about we do it over Zoom call, right? What about I do it with you right now? Yeah. Now, unfortunately, you can't switch on your camera, so we can't do it on you. And this is why we want to get our helpers back. And we're going to demonstrate how we are going to measure someone's pulse rate through a Zoom call. Okay, now, at this point, I would like to invite Miranda to switch on her camera. Hi, Miranda.
Hello.
Hi, Miranda. So Miranda has this program that we can use to measure pulse rates through the Zoom call. Okay. Now, Ethan, can you switch on your camera? And okay.
Hello.
Hi, Ethan. Ethan, where are you at the moment?
Well, I'm right now in China, in my home.
In China, right? So
yes.
I'm in the UK, in London. Miranda, where are you?
I'm also in London.
You're also in London. Okay. So what we're trying to do next is Miranda is trying to use this computer program to measure Ethan's pulse rate over the Zoom call. And he's very far away. And let's see whether we can do this. Okay, Miranda.
So I'm just gonna start by sharing my screen, and if we first of all, so we can see the thumbnail of Yufan's video. So this is just a static version of it right now. So if I choose to select this region of the screen, that means that I'll be focusing on the bit where his video actually is. And in the first instance, we're not going to do a finger. We'll just show you. So Yifan, if you just like move your arms around, you can see that as he moves, you know, the amplitude of the signal that we measure from the camera varies. Obviously, we're not going to get some kind of pulse rate from that, but that's just to demonstrate how the variations in the signal change the result. And so now if we, I'm just going to reselect that region. Yifan, if you could put your finger over your camera and just make sure you hold it nice and steady.
Okay.
Yeah, okay, so if I'm going to start, I'll start it now, and hopefully, yeah, you can see these, we'll see it better afterwards, but you can see these variations already in the amplitude of the signal, which is coming from his pulse rate. It's not the best one currently. We'll redo it just now. You can see it was strong at first. Yifan, take your finger off for a sec. You can see that it was a good signal at first, and I think his finger shifted. So you can see that it's sensitive in general to if there's any background light coming in, then that can affect the overall amplitude as well. So if we try that, let's try that again.
Yes.
I'll just select here. Maybe I'll select the smaller region. Okay, you want to put your finger over? Let's see. Yeah?
Okay.
I'm going to start now. We'll see if we can get a clearer signal this time. Oh yeah, look at that, that's nice. So you can see the actual, the shape of the pulsation waveform coming in. Yeah, that's much better. There you go, you can take your finger off. So you can see here, you can see clearly that the amplitude is varying with his pulse. We've also got this sort of background variation. And then after we do this Fourier transform that Terence explained about, we can see we've got one clear peak at about 1.4. So if we multiply that by 60, then we get an estimate of Yifan's heart rate of about 82, which is a sort of normal kind of level. So that's good, Yifan, you're healthy.
Yeah. Good to hear that.
And we can go even one step further. So Terence has talked about how you do it based on using the finger, but it's even possible in the same way as there's a variation in blood flow through your finger, there's a variation in blood flow through your face. So this was definitely less reliable, at least over a Zoom call. But what we're going to do is we're going to see if we can measure Yifan's pulse rate by just using the actual video of his face. So if you can put your hands under your chin.
Okay.
Yeah, and then tilt your head up a bit. Yeah, okay, great. And now if I just close, I close all of that. So if you can hold perfectly still, keep your eyes closed. I'm going to select, if you can see here, I'm just going to select just his face this time because we don't want to have too much background. So you ready, Yifan? Stay there.
Okay.
Yeah. So if we just, you won't see the pulsation here as clearly because it's a much smaller variation, but we can see he's doing a good job at staying nice and still, which is good. We'll see if we can actually extract a signal from it. You can move again now. Yeah,
okay.
Not so good this time. I think it varies. As you can see, this is a much less reliable method because there's so many more factors that could be affecting the signal. So like even just slight changing background illumination, which is why in general using that finger method is much more reliable.
Okay, excellent. Thank you very much, Miranda and Yifan. So we are going to wrap up now, but before we finish, I just want to tell you a little bit about our course. Now, in fact, what you've seen just now about using a digital camera to measure pulse rates, this is in fact part of our syllabus. So at UCL, in our biomedical engineering course, we have this scenario weeks. So these scenario weeks, we have 6 of them throughout the first and second year. So each scenario is 1 week long, and students basically come together to do a group projects. And for the first scenario, for the past few years, students have been creating healthcare apps. Okay, so we use different computer languages in earlier in the course. Between 2015 and 2019, we use a language called BASIC for Android. And then in 2020, we use MATLAB Simulink. So you can see that students showcasing their apps that they developed. So what happened is these students, they didn't know anything about app programming before the scenario week, but then we have a special way to teach them app programming on Monday and Tuesday, and they practice it, and then by Friday, they managed to develop their own healthcare apps. And I just want to share with you some of the apps that they've developed. So what happened is after they've developed their apps, we want to make sure that app actually gives us a reliable heart rates reading. So that's why we use a pulse oximeter to measure the heart rates of the subject independently. And we compare the heart rate results between their apps and also the pulse oximeter. So this is a student doing some exercise, and we want to see whether the app can actually track the heart rates, even if the heart rate is actually higher than normal. And as you can see, sometimes students also put in their own user interface. You know, they put in some graphics there to make it more interesting. And so this is another photo of students testing their own app. And you can see that they are very creative. They come up with all sort of graphical user interface. So a very interesting background here. And then some ECG signal in the background. And this is actually a very nice one because this is actually animation. The heart was actually pumping. And then there's another nice user interface here. I think the student designed this logo themselves. Now, actually, beyond pulse rates, students actually make use of the pulse rates and come up with some applications. Now, this is called Junior Detective App. This is just kind of a game for kids. So what happened is you are supposed to use this to find a burglar. You use the torch to find the burglar. And then you use the pulse rate detector as a lie detector to interrogate the burglar. Okay, if the heart rate is too high, then that means they're lying, apparently. And then there's also stress detector. So it's just simply, if your heart rate is very high, then that means you're very stressed. Okay, not sure whether it's very accurate. And then there's love detector. Okay, so apparently if your pulse rate is 73 beats per minute, then the comment is there are other people out there for you. Okay, whatever it means. And then there are some other interesting ideas, like this is a Prang App shock detector. So apparently what happens is they show you a nice looking kitty photo and they measure your pulse rate. And then they show you a horrible picture and see how much, you know, how high your heart rate gets to, you know, measure the difference. And then there's this coffee counter. Apparently, the more coffee you drink, the higher your heart rate. But this is just some of the examples that they came up with. Okay, so that's the end of my talk. I hope you've learned something about pulse rate detection and a little bit about our course as well. Okay, so time for some questions. So if you have any questions, you can make use of the chat box, okay? So you can type your questions in the chat box. Okay, now, so I've received some questions. Now, let me just go through it one by one. I think there is one about, is there a large focus on programming in this course? I think the answer is yes. We do actually have quite a lot of programming. I think this is true for almost all the engineering courses right now, in the UK at least. The reason is because programming is very important. I mean, the world is full of AI application, automation. So in our course, we are also emphasis on AI as well. So in fact, this year, our scenario one, we change it to AI application. So we get students to develop an app that will identify certain objects using the webcam. So there's quite a bit of programming. But on the other hand, this is not a computer science course. So although there's quite a bit of programming, it won't be all about programming. Okay, so we only teach you some scientific programming that will allow you to develop apps, may not go too deep into the programming. If you are really interested in programming, there is an option to choose programming as your minor, which is a collection of 3 modules in second and third year. You can choose different minors. One minor you can choose is programming. Okay, so now I have quite a few questions. All right, so now let me just answer one question about Fourier transform. How does the Fourier transform turn a signal in the time domain into a signal in the frequency domain? Okay, so this is actually a very good question. Now, what happened is as long as we have a periodic signal, no matter what kind of periodic signal, as long as they're periodic, we can actually use many different sine waves at different frequencies to model it. Okay, so I'll give you an extreme example. Yeah, if you have a square wave, okay, you can actually use lots of different sine waves of different amplitudes and frequency to model it. Okay, so if let's say we have a perfect sine wave, and then Fourier transform basically is going to fit a lot of sine waves of different frequency. If for a particular frequency which doesn't match with your signal, your sine wave, then the coefficient will be small until you have a sine wave that matches your given sine wave perfectly. In that case, the coefficient will be high. Okay, I think the exact detail is slightly difficult to explain like this. But that's the main principle. Basically, Fourier transform fitting lots of sinusoidal signals at different frequency, okay, and see how which of the sine waves matches with your given waveform. All right. Okay. Another question is how does food affect the heart rates? Okay, so wow, this is beyond my domain. We are kind of biomedical engineer. I'm not too sure about food affects the heart rates. This is something maybe for the physiologists to answer. I think our aim is to provide the best technology for clinicians, physiologists, biologists to understand the human body. Okay, so another question. Do I have to be good at biology to apply at UCL in bioengineering, or is math, physics, and chemistry sufficient? Yeah, very good question. In fact, math and physics are sufficient, not even chemistry. Okay, so you don't need to be very good in biology to apply to our biomedical engineering course. That's why our entry requirement is only about math and physics. We don't mind whether you have biology at all, in fact. So the biology bit, we are going to teach you in the course, but then you do need to have some aptitude in math and physics. So that's why we really would like you to be good at math and physics in order to apply to this course. Okay, another question. What difficulties do the manufacturers of the smartwatches face when trying to get medical grade licensing and approvals so that their products can be used with the same level of confidence as real medical equipment? This is actually a very good question. In fact, getting regulatory approval is a big problem for medical devices. That's why a lot of new medical devices, for example, recently I come across electronics wireless stethoscope, a very nice device, totally wireless. You can use it to measure your heart rates or heart sounds. You can measure the heart sound and then you can record the heart sound onto your smartphone app, right? Now that particular device, if you want to make it a proper medical device, it takes a long time. Instead, they market it as a fitness device. In that case, this is not really for healthcare purpose. This is for fitness purpose. In that case, the regulation is more relaxed and they're able to make it as a marketable product quicker. But then if we want to actually say some like a smartwatch as a medical equipment, it actually takes longer and more data to go through this very rigorous process in order to get the medical grade licensing. Okay, so it takes a lot of time, money, and effort to actually get medical grade licensing. Okay, wow, okay, we've got quite a lot of questions on the chat box. And so one question is, what other things come up on the syllabus of this course? Yeah, so biomedical engineering is a multidisciplinary course. So you also learn about medical electronics and biomechanics and anatomy and physiology. And as I mentioned earlier, in your second and third year, you can choose a minor stream, we call it. So minor stream consists of 3 modules in the second and third year. And this minor stream is organized by other engineering departments, for example, computer science or maybe biochemical engineering. So you can then pick some modules on, let's say, regenerative medicines, or maybe some students are interested in languages. They can choose languages as their minor, or a lot of students like to take management and accounting as their minor stream. So that's a lot of different modules that you can choose to do. And but then for biomedical engineering related subjects, they are mostly medical electronics, biomechanics, and also programming. Okay. Okay, I see. Okay, so okay, so I have one question sent to me. can I study other engineering areas too with this program? Okay, so okay. Okay, so yes, I have just answered this question. This is about can you study other engineering areas? Yes, you can. This is through the minor stream arrangement. Okay. Okay, sorry, I think I didn't press the correct button. I hope all the questions asked are now visible to you. Okay, so any other questions? Okay, so you can put down your questions in the Q and using the Q&A box. By the way, we do have a poll, online poll. So if you can maybe fill in the poll, that would be very helpful to us. Okay, so if you have any other questions, you can enter it in the Q&A box. So there's a poll going on. If that's okay with you, perhaps you can fill in the poll. Okay, right. Thank you very much to attend our taster session, Spring into STEM. And I hope you enjoy this talk, and I hope you enjoy our demonstration as well. Okay, so maybe we can finish here. So thanks for joining us, and I hope you apply to our course. Thank you. Bye.